Hi students, നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ L of xyയുടെ സ്ട്രക്ചർ കണ്ടു. L of xy എന്ന് പറഞ്ഞാൽ ഇറ്റ്സ് എ വെക്ടർ സ്പേസ് പ്ലസ് എ റിംഗ്. Such kind of structures are known as algebras. ഈ ക്ലാസ്സിൽ നമ്മൾ ഓപ്പറേറ്റർ നോർം L of x, y ഡിഫൈൻ ചെയ്യാൻ പോവുകയാണ്. അതിനു മുമ്പായിട്ട് വെക്ടർ സ്പേസ് Rnന്റെ ഇന്നർ പ്രൊഡക്റ്റ് സ്ട്രക്ചർ ഒന്ന് പരിശോധിക്കാം. നമുക്കറിയാം Rn is a vector space under component wise addition and scalar multiplication. There is one more operation possible in Rn. It is called inner product or dot product in Rn. So take any two vectors x equal to x1 etc. xn and y is equal to y1 etc. yn in Rn. Then x dot y or x inner product y is defined as x1 y1 plus etc. plus xn yn. നിങ്ങൾ പ്ലസ് ടു ലെവലിലൊക്കെ പഠിച്ച എ ഡോട്ട് ബി ഈക്വൽ ടു മോഡ് എ മോഡ് ബി into cos theta, where theta is the angle between the vectors a and b measured counterclockwise. അതും ഇതും ഒന്ന് തന്നെയാണ്. a inner product b equal to a1 b1 plus etc plus a n bn എന്ന് പറയുന്നതും a dot b equal to mod a mod b cos theta എന്ന് പറയുന്നതും both are the same. ഈ ഇന്നർ പ്രൊഡക്റ്റിന് ചില പ്രോപ്പർട്ടീസ് ഉണ്ട്. ഫോർ എക്സാമ്പിൾ എക്സ് ഡോട്ട് വൈ പ്ലസ് സെഡ് ഈക്വൽ ടു എക്സ് ഡോട്ട് വൈ പ്ലസ് എക്സ് ഡോട്ട് സെഡ്. എക്സ് പ്ലസ് വൈ ഡോട്ട് സെഡ് ഈക്വൽ ടു എക്സ് ഡോട്ട് സെഡ് പ്ലസ് വൈ ഡോട്ട് സെഡ്. അങ്ങനെ ഡിസ്ട്രിബ്യൂട്ടീവ് പ്രോപ്പർട്ടീസ് ഉണ്ട്. പിന്നെ എക്സ് ഡോട്ട് സി വൈ ഈക്വൽ ടു സി ടൈംസ് എക്സ് ഡോട്ട് വൈ, ആ പ്രോപ്പർട്ടി ഉണ്ട്. വേറെ സി ഇസ് എ സ്കേലർ. അതുപോലെ സി എക്സ് ഡോട്ട് വൈ ഈക്വൽ ടു സി ടൈംസ് എക്സ് ഡോട്ട് വൈ, വേറെ സി ഇസ് എ സ്കേലർ. പിന്നെ വേറെ പ്രോപ്പർട്ടി എന്ന് പറയാൻ എക്സ് ഇന്നർ പ്രൊഡക്റ്റ് എക്സ് ഓൾവേസ് ഗ്രേറ്റർ ദാൻ ഓർ ഈക്വൽ ടു 0 ആൻഡ് എക്സ് ഡോട്ട് എക്സ് ഈക്വൽ ടു 0 ഇഫ് ആൻഡ് ഓൺലി ഇഫ് എക്സ് ഈക്വൽ ടു 0. 0 മീൻസ് 0 വെക്ടർ. ഇവിടെ ഒരു കാര്യം പ്രത്യേകം നോട്ട് ചെയ്യേണ്ടത്, ഈ ഇന്നർ പ്രൊഡക്റ്റ് എന്ന് പറഞ്ഞാൽ അത് Rn ക്രോസ് Rn എന്നിൽ നിന്ന് ആറിലേക്കുള്ള ഒരു ഫംഗ്ഷനാണ്. എക്സ് ഈസ് കമ്മിങ് ഫ്രം Rn, വൈ ഈസ് കമ്മിങ് ഫ്രം Rn. സോ എക്സ് ഡോട്ട് വൈ എന്ന് പറഞ്ഞാൽ there are two input variables at a time. So the domain is Rn cross Rn. And what is the codomain? Look at this. This is a real number. So codomain is set of real numbers. So dot product is a mapping from Rn cross Rn to R, satisfying the above set properties. One more property is there which I forgot to mention. X dot y is the same as y dot x. Our property. Now once you have a inner product, there is a norm induced by this inner product, and it is defined as norm of x is equal to non-negative square root of x dot x. That means non-negative square root of x1 square plus etc plus xn square. So this will denote the distance of the vector x from the origin, and this norm satisfies all the properties required for a norm. Basically, norm of x greater than or equal to 0 and norm of x equal to 0 if and only if x equal to 0. Next property, norm of x plus y less than or equal to norm x plus norm y. And finally, norm of cx is mod c times norm x, where c is a scalar. Next, Cauchy-Squartz inequality. ഇതൊരു റിയൽ നമ്പർ ആണെന്ന് പറഞ്ഞു എക്സ് ഡോട്ട് വൈ. സോ മോഡുലസ് ഓഫ് എക്സ് ഡോട്ട് വൈ ലെസ് ദാൻ ഈക്വൽ ടു നോർം എക്സ് ഇൻറ്റു നോർം വൈ. ഈ റിസൾട്ട് നിങ്ങൾ റിയൽ അനാലിസിസ് 1 അല്ലെങ്കിൽ ലീനിയർ ആൾജിബ്ര കോഴ്സിലൊക്കെ കണ്ടിട്ടുണ്ടായിരിക്കും. ആൻഡ് ദർ ഈസ് എ കൺസെപ്റ്റ് ഓഫ് ഓർത്തോനോർമൽ ബേസിസ്. സോ what is meant by orthonormality? A set is said to be orthonormal if every element in that set has norm equal to 1 and one more thing, two more things. X dot y equal to 0 if x not equal to y. It is called orthogonality. A condition meet cheyanam. Third thing, it should be a basis. So if all these conditions are met, then that set is called an orthonormal basis for Rn. So the standard orthonormal basis for Rn is E1, E2, etc. En. Remember here norm of E1 is 1, etc. Norm of En equal to 1. And E1 dot E2 will be equal to 0. Or in general Ei dot Ej equal to 0. And this is a basis. So therefore this is an orthonormal basis for Rn and it is called standard orthonormal basis. Next we are going to define what is called operator norm of an element L in A in L of Rn comma Rm. So A is an operator, is a transformation from Rn to Rm. Now look at the set of all norm of A of x. So this is a real number such that, so this line stands for such that x belongs to Rn and norm of x less than or equal to 1. Look at this set. So A is from Rn to Rm. So x is in Rn. So A of x is in Rn. So this norm is in Rm. This norm is in Rm and x is in Rn. So this norm is in Rm. So these things are understood. Look at this set. X varies in the unit closed unit ball of Rn. Norm x less than or equal to 1 means closed unit ball of Rn. We will show that this set is bounded. This set is, so this is a subset of real numbers because norm of A of x is real number. This is clearly bounded below by 0 because norm is always greater than or equal to 0. Now we will show that this is bounded above. For that, take any x in Rn, norm x less than or equal to 1. Since x is in Rn, it can be written as a linear combination of the standard basis elements E1, etc. En. So x is equal to summation Cj Ej. Now, since norm x less than or equal to 1, it means that mod Cj are less than or equal to 1. Why is that? Because if mod Cj is greater than 1 for some j, then what about norm of x? Here x is C1, C2, etc. Cn, that n tuple. So norm of x will be square root of C1 square plus etc. plus Cn square. So if mod Cj is strictly bigger than 1 for some j, then it means that norm x would be bigger than 1. That is not true. So norm x must be less than or equal to 1 if x is in Rn with norm x less than or equal to 1. We have mod Cj less than or equal to 1. Now A is linear. So A of x is equal to sigma j equal to 1 to n Cj A of Ej norm of A of x is equal to sigma Cj A of Ej norm of that. I forgot to write norm here. I just put modulus. This is a mistake. So norm of sigma Cj A of Ej, but norm less than or equal to sigma mod Cj norm of A of Ej. Why is this? Because of the property of norm. Norm has the property norm of x plus y less than or equal to norm x plus norm y, and norm of Cx is mod C times norm x. Using those two properties, I will get this quantity less than or equal to this. But mod Cj always less than or equal to 1 for all j. So this summation less than or equal to sigma norm of A of Ej. Now look at this number. It is independent of x. For all x in Rn with norm x less than or equal to 1, norm of A of x is maximum this much. This is independent of x. So this is an upper bound for my set in my previous slide. So sigma j equal to 1 to n norm of A of Ej, that is an upper bound for this set. So that set is bounded above. Therefore, we can look at its supremum, and we define norm of A to be supremum of norm of A of x such that x varies in Rn, norm x less than or equal to 1. This number is called operator norm of A. മനസ്സിലായി എന്ന് ചോദിക്കുന്നു. Now we will see some properties of the operator norm. First of all, we have norm A greater than or equal to 0 and norm A equal to 0 if and only if A equal to the 0 operator. Proof. First of all, we will see norm A greater than or equal to 0, but then that is clear because norm A is defined as supremum of this set. Norm of A of x, norm x less than or equal to 1. So 0 is a lower bound for this set. So 0 less than or equal to norm of A or norm of A greater than or equal to 0. Now we have to show norm A equal to 0 if and only if A equal to 0 operator. So assume A equal to 0 operator. Then clearly by definition of norm of A will be equal to 0. This was the definition of norm of A. If A equal to 0, then A of x will be 0 because A is linear. Norm will be 0, supremum will be 0. So norm of A equal to 0. So this part is proved. Conversely, assume norm A equal to 0. We have to show A equal to 0. 0 operator. So since norm A equal to 0, by definition of norm of A, we have norm of A of x equal to 0 for all x in Rn with norm x less than or equal to 1. Because if supremum equal to 0 and 0 being a lower bound of that set, norm of A of x will lie in between 0 and that supremum. But that supremum here is 0. So norm of A of x will be equal to 0 for all x in Rn with norm x less than or equal to 1. This will tell you that Ax equal to 0 for all x in Rn with norm x less than or equal to 1. That condition norm x less than or equal to 1 is still there. We have to get out of that restriction. And we have to say Ax equal to 0 for all x in Rn. അത്രയും പറയാൻ സാധിക്കണം. അങ്ങനെ പറഞ്ഞു കഴിഞ്ഞാൽ we can say A is the 0 operator. So to get rid of this, what we will do, take any x in Rn. And if x is the 0 vector, then Ax is A of 0 equal to 0. We are done. And if x not equal to 0, so you take any vector in Rn, it may be 0 vector, it may be a non-zero vector. So if it is a non-zero vector, its norm need not be less than or equal to 1. So what we will do, we will take y is equal to x by norm x. Then norm of y will be equal to 1 by norm x into norm x equal to 1. So y is here. Norm of y equal to 1. Therefore, by definition, norm of A of y is less than or equal to its supremum. Norm of A. Supremum of that set, which is norm of A. Now substitute for y. What I will get? Norm of A of x by norm x less than or equal to norm A. So 1 by norm x comes out. We have 1 by norm x times norm A y less than or equal to norm A, or norm of A of x is less than or equal to norm A into norm x. Clear? Now look at this inequality. If x equal to 0, right side is equal to 0, and Ax equal to 0, left side is also equal to 0. So this inequality is true even if x equal to 0. Thus we get norm of A of x less than or equal to norm A into norm x for all x in Rn. Even if x equal to 0 or non-zero, doesn't matter. You have this inequality. So this inequality is very important. We will be using it several times. Now what is our assumption? Our assumption was norm A equal to 0. So norm of A of x must be equal to 0 for all x in Rn, or that A is the 0 operator. So we have proved it. മനസ്സിലായി എന്ന് വിചാരിക്കുന്നു. Second property, norm of CA is mod C times norm A, where C is a scalar and A in L of Rn, Rm. Its proof is left as an exercise. We can easily do it by property of supremum. Third property, norm of A plus B less than or equal to norm A plus norm B. We will prove it. Proof you can read from the slides, or I will explain. Norm of A plus B of x, start with that, equal to, by definition of A plus B of x is Ax plus Bx. Norm of that less than or equal to norm Ax plus norm Bx. Less than or equal to, by our inequality 1 in previous slide. This is inequality 1. Norm Ax less than or equal to norm A norm x, and norm Bx less than or equal to norm B norm x, and sum of that equal to norm A plus norm B times norm x, which is less than or equal to norm A plus norm B for all x in Rn with norm x less than or equal to 1. Okay, so this is an upper bound. Norm A plus norm B is an upper bound for the set norm of A plus B of x such that x varies in Rn, norm x less than or equal to 1. But what is the least upper bound of that set? It is precisely by definition norm of A plus B. So what is the relation between this upper bound and the least upper bound? Least upper bound is less than or equal to any upper bound. So what is least upper bound? Norm of A plus B. So norm of A plus B less than or equal to norm A plus norm B. അതാണ് നമുക്ക് പ്രൂവ് ചെയ്യേണ്ടത്. Fourth property, norm of AB less than or equal to norm A into norm B. Proof is left as an exercise. I can give you another exercise. I'll type here. Show that operator norm. Is uniformly continuous. So just a second. Define d of a comma b equal to operator norm of a minus b show that D is symmetric in L of Rn, r to the power n, comma r to the power m, and operator norm is the metric. And A is uniformly continuous. And the linear transformation. So this is also an exercise. Thank you.